Well, I can't be sure, but you may be thinking at this point, I thought I was taking a class on adaptive filters, and here we have yet another lecture module on matrix math. Well, we'll get there eventually. We do have a few other things to go through so that when we get to the adaptive filters, it'll be smooth sailing. You probably remember positive definite matrices. A matrix is called positive definite if any of the conditions below apply. The first one is all eigenvalues are positive. If that's the case, and we have a positive definite matrix, or if we don't want to find the eigenvalues, we can just look at all possible vectors x. There's an infinite number of them, so this might take some time, or maybe there are better ways about it, but we take for any x that's not 0, if x transpose ax is greater than 0 or positive, then we have a positive definite matrix. Finally, we could just find the determinant of the matrix, and if it's greater than 0, then we have a positive definite matrix. So we should note that these conditions are equivalent. If any of these conditions hold, all of them hold, and we have a positive definite matrix. Well, sometimes we don't have a positive definite matrix, but we might have a positive semi-definite matrix, sometimes called a non-negative definite matrix. And the conditions here are pretty much the same as for a positive definite matrix. The difference is all eigenvalues have to be greater than or equal to 0 instead of strictly greater than 0. Likewise, x transpose ax is greater than or equal to 0 for all x not equal to 0. And the determinant has to be greater than or equal to 0. As above, all of these conditions are equivalent. Well, if we have a positive definite matrix, it's going to be invertible. If we have a positive semi-definite matrix, it may not be invertible. Well, when is it not invertible? It's not invertible if any of those greater than or equal to are actually equal to 0. In other words, all it takes is one 0 eigenvalue and the matrix is not invertible. Well, we can use these properties actually to figure out how to solve for our eigenvalues. It turns out, as I'd mentioned earlier in a previous lecture, the easiest way to solve for the eigenvalues is to use the eig function in MATLAB or Python. But sometimes it's helpful to know how to do this, especially if we're dealing with a small matrix, a 2 by 2 or something like that. So let's assume that we have u, I, and lambda I are respectively an eigenvector and the associated eigenvalue with that vector of matrix A. So matrix A will have, if it's an n by n matrix, it will have n eigenvalues and n eigenvectors. They aren't necessarily unique, but there are conditions in which they would be unique. For example, our favorite, easiest matrix to work with, the identity matrix, has, if it's an n by n identity matrix, it has n eigenvalues, but each of them has a value of 1, so they're not unique. However, it's possible to find n linearly independent orthogonal eigenvectors associated with that matrix. And we're hoping for cases like that. We'll discuss later when that might happen. But for now, assume that we have these eigenvectors, then eigenvector and eigenvalue, then we know that A times ui is going to be lambda I times ui, just by the definition. If this is the case, we can subtract lambda ui from both sides, and that should evaluate to the 0 vector. Well, if that evaluates to the 0 value, well, actually first let's pull out ui. So looking above at our properties, we can take, we have here something that violates the positive definiteness, if you will, of the second condition. We can take the determinant then, and we know that it's going to be equal to 0. As a result, all we have to do, and this is a big ask, whoops, is find the determinant of matrix A minus lambda I times I. And that's going to give us a polynomial equation. It's called the characteristic equation. By solving that equation, we can find, if we solve it for all the roots, we'll find all of the eigenvalues, the lambda i's. So next, you can see I have about a third or a quarter of my page left, and we're going to sum up all of matrix calculus in that space. There obviously is more, and actually in the course website I've posted a nice little workup that describes some of the other aspects of matrix calculus. It turns out, since matrices or matrix operations are linear operations, or quadratic sometimes if we have an x transpose ax, for example, that the calculus is fairly straightforward. So suppose we have B is equal to A transpose X, where A is a column vector and X is a column vector. So the resulting inner product is going to be a scalar B, and that can be written as B is equal to A1 X1 plus A2 X2, so on and so forth, up to AN XN. So where the A sub i's and the X sub i's are the elements of A and X vectors respectively. Then we can find the partial derivative of B with respect to any X element. And it will be just the corresponding A element. Okay, that's straightforward. Let's make it a little more complex. Often we want to find the gradient of B with respect to X. And we'll write that using the nabla notation, where the gradient with respect to X of B is going to be defined as the column vector of the partial derivatives of B with respect to the X elements. And we've just above defined what each of those are. This ends up being the column vector A, as we've seen before. So this is kind of nice. This is what you might expect with just scalar operations. If we had B equals AX, where A and B were, or A and X were scalars, then the derivative with respect to X of A, or of B rather, is going to be just A. So we get the same type of thing here. So it follows some intuition. Now, since B is a scalar, B is going to be equivalent to B transpose. And that yields this nice little property, that the gradient of A transpose X is going to be equal to the gradient of X transpose A, which in both cases is just equal to the column vector A. That throws a few people off, in my experience, but just remember it all comes down to the fact that what's in the parentheses is a scalar, and so the transpose doesn't matter, and the gradient is defined as a column vector. Okay, one more important part of matrix algebra, calculus rather, and that's going to be the quadratic form. For the quadratic form, that is, B is equal to X transpose AX, we once again have a vector B, and we can define the gradient with respect to X of B as AX plus A transpose X. So I won't go through that. It's something that you could do easily in your own time. Maybe you have a quiet, boring Friday night, and so you pull out a piece of paper and just run through the definition of the gradient of B as shown over there on the left, and you'll be able to work this out. One important thing to note is that if A is symmetric, then A is equal to A transpose. And so we get that the gradient with respect to B, or the gradient of B with respect to X, is 2AX. And if we had A as a scalar and X as a scalar, we would have had B is equal to AX squared, and the derivative would have been 2AX. So once again, this looks like the kind of a natural outgrowth, if you will, of scalar calculus. But this property only holds for symmetric matrices A.